Thank you for coming. Tonight's meeting, we are in the Ottawa-Valley chapter of ASHRAE. If that doesn't resonate with you, you might be in the wrong room. I'm Daniel Redmond, I'm your president.
Yay.
Thank you, Kevin. I'd like to start by introducing the Board of Governors and the Executive. So Jacob Huff, Board of Governors, he's not here this evening. We have Chris Crawley, Board of Governors, also not here this evening. Celine Barabo, Governor, Celine is here. Peter Shawwood, Governor, also here. Joe Delaval, Governor, also here. Adrienne Matani is our Secretary. Adam Moons is our Treasurer. And Aaron Dobson, who unfortunately is sick this evening, is our President-elect. Our past President is Adam Graham. And Adam, please stand up so people will remember what you look like. I would also like to introduce or to let everyone know that we are delighted to have a Society officer with us this evening. Daryl Boyce, the Society President-elect, who will be sworn in June as the next President of ASHRAE, who hails from the Ottawa-Valley chapter. It's pretty exceptional that in all of the years of ASHRAE, that not only Daryl will be the 6th president from Canada, but to have a president from our chapter coming from where we are. It just kind of shows how anybody involved with ASHRAE, you can really take it as far as you want to take it and get as involved as you want to get. 60,000 members worldwide, and Daryl will be overseeing it. It'll be a busy year, but I'm sure you'll enjoy it.
Better.
I'd now like to call upon Adrienne Matani to introduce the guests.
So the guests for the evening are Kevin Belusa, Eric Hilkeast, Ryan Harani, Frederick Dion, Connor Patterson, James Owen, Marco Pillock, and Jim Watson.
Thank you very much, Adrienne. Now I'd like to call upon Andrew Brown to introduce the new members.
It gives me great pleasure to introduce the following new members. Michael Bartko, Matthew Levesque, Alex Lapointe, Kareem Sadi, Sarah Abraham, Zarna Kakadia, Muhammad Wakas, Jean Cardinal, and Mafonbon Etukudu. Thank you.
Thank you very much, Andrew. Now, I mentioned earlier that Aaron Dobson is not with us tonight. Aaron is our Research Promotion Chair. And he did want me to pass on that so far this year we have raised 58% of our goal. Our goal this year is $34,300. Adam Moons, who's at the back, is raising funds for RV tonight and selling raffle tickets, which are
4 tickets to the Senators versus Buffalo on the 26th of March with 2 parking passes. They're really great seats, donated by Walmart.
fantastic. Thank you very much. If anybody has not yet purchased tickets from Adam, he's the guy at the back that just shouted out at everybody and the guy that's holding a pile of money. What? So, I mean, tickets. So please, give often, give lots. No, research promotion, as I've said before, research promotion really is the mechanism by which we advance the standards and the technology that really our industry benefits from every day. This is the mechanism by which ASHRAE raises funds to further research into our industry. And realistically, our environment here in Canada, here in Ottawa even, we're lucky that we actually benefit from a lot of that research money. All of the money that we donate towards ASHRAE research promotion stays in Canada and funds research done here in Canada. I would now like to call upon Abby Saunders to give a talk about nominations.
Hello everyone. I just want to take a moment to reintroduce Steve Moons and myself as the chairs for the Honors and Awards and the Nominations Committees this year. The Nominations Committee is responsible to build the chapter leadership for tomorrow. The Nomination Committee helps to shape the direction of the chapter, and in that we try to ensure that the very best people are in the position to advance the chapter and service our members' needs. The time has come where we need to consider nominations for next year's executive and the Board of Governors. On behalf of the Nominating Committee, I'm pleased to announce the following eligible members to hold office as Chapter Executive for the 2018-2019 ASHRAE season. President, Aaron Dobson. President-elect, Adam Moons. And Treasurer, Adrian Matani. Positions that we are seeking nominations for at this time include Secretary and the Board of Governors. I'd like to call for a motion to open nominations for the 2018-2019 season. First by Nick Lee, and second, it's got to be an ASHRAE member. Kevin, are you?
I am a member, not from this chapter.
Gemma, thank you. Perfect. So with that, the 2018-2019 ASHRAE nominations are open. To be considered for a Board of Governors, nominees must be chapter members in good standing with society, and they must also have consented either orally or in writing to have their name put forward. The election to chapter officers is a distinct honor bestowed on ASHRAE members by their peers in anticipation of their dedication to the continued success of the chapter. The nomination committee will be meeting in the upcoming weeks to determine who we're going to put forward for the open positions. Nominees will be announced at the May meeting, and the installation of the new board and executive takes place at the May meeting. If you have any questions related to nominations or awards, please feel free to reach out to either Steve Moons, myself, or anyone on the executive for that matter. Thank you.
Thank you very much, Abby. It is truly an exceptional ride, so I encourage anybody who is considering this, take advantage of it. It's a fantastic opportunity. I'd like to call upon Peter Shawwood to come up and say a little bit about students. Our theme this evening is students. We have a number of students in attendance, and
thanks, Dan. Evening, everybody. So my name is Peter Shawwood. I'm here on behalf of Liz today. She couldn't be here with us just to talk about student activities and some of the stuff that we've been doing this year. Of course, March is the theme, student activities. And this chapter does a lot for students in Ottawa. The Carleton branch, of course, is our strong one. We've got Jason, who's been doing that as the president for years and has come up with a nice new transition plan. It's going to bring in our new president at Carleton. That's going to be Dan. He's sitting over there right now. Give him a round of applause. Chapter definitely appreciates the service that you're going to put in, and hopefully you get a lot out of it. I know Jason's enjoyed it, and Dre's spoken highly about it. But we'll have your back, and we'll support you with everything that you possibly need. So please, talk to us about some of the stuff that you want to do and any initiatives, and we'll do what we can. Other than that, I think we have about 7 students here tonight, which is great. The more the merry. Another thing I'd like to see is just how students integrate into the chapter and then into the industry quickly after. I mean, I've been integrated into the HVAC industry because of this chapter. That was a long time ago. I see a couple faces here who I was looking at in the classrooms not too long ago. We're now in industry, which is great. It's an industry that doesn't get as much exposure as it could, say for the normal channels of Discovery Channel or some of the teachers who like to talk about the aerospace industry or automotive things or spaceships and that kind of stuff. So good promotion that we see from ASHRAE. So a big thanks to the chapter for all of that, and for the other things that we do, like the student award. That's I know a big cost, as well as the awards that we give to the science fair every year. It's 3 $200 prizes. I know the students there appreciate it. It's great for us to go out and see what students are up to in the HVAC related projects. So good stuff, and big thank you to everybody.
It's a fantastic opportunity for students to liaise with industry professionals, and an opportunity to get to know more about an industry that really does touch everybody, every day, everywhere. I mean, this industry exists everywhere that there are people. We we build buildings for people so that they can do things in buildings. And essentially, wherever there are people, there is this industry. I'd like to call upon Adrienne Matani to talk about the recent career fair.
So earlier this month, first week of March, we had a career fair held at Carleton. It was very well attended. We had 14 booths from different areas of industry, including contractors, suppliers, and a lot of consultants as well. Also, one sponsor from Ainsworth, which we're very happy about. We had over 150 students in attendance, which is really great. It was a nice mix of Carleton, Ottawa U, and Algonquin. We're hoping to get out more Cégep and La Cité students in the future, but they still have a little bit farther to come, unfortunately, when we hold it at Carleton. But it's something we're working towards in the future. So, that's it. Thank you very much.
Thank you very much, Adrienne. We also had the Ottawa-Valley Chapter Curling Bonspiel on March the 8th. And it was a fantastic event, fantastic afternoon. We raised $1,400 towards a local charity and $1,050 towards ASHRAE Research Promotion. The winning team was Total HVAC 1, and I have to say 1 because, Mark, how many Total HVAC teams were there? Was it like 8? No, I believe there were 3 Total HVAC teams. And I'm picking on Mark because Mark got to take home the trophy. So the winning team had Mark Gall, Langdon Liebert, Tom Leroy, and Josh Bates. And congratulations, Mark, and to your team. And I'd now like to call on... Congratulations, Mark. I'd like to get Adrienne back up here to talk some more about, what is it listed? No, to talk about seminars. Thank you.
Hi again. So last Wednesday we had a seminar put on by Ralph Kaizen, who is out of the Vancouver area, but he works for ASHRAE across the society, and he does leadership weekends. And we were very fortunate that we were able to get him out here to Ottawa, and he gave a presentation on business development. We had great attendance, and we were in the master boardroom. And he talked to us about different ways to approach business development, some different key strategies to go over, as well as just how to communicate with different people, because a lot of business development is communication, and that's a great skill for engineers to have. So it was a fantastic presentation, and it was great to have Ralph in town. I'm also going to briefly talk about an upcoming seminar we have coming up next month. It's going to be held or put on by Bjarni Olsen, who is ASHRAE Society President last year. He's going to be coming to Ottawa on April 17th. It's a Wednesday. It's a full-day seminar, and it'll be on the European approach to decrease energy consumption in buildings. So he's from Denmark, and he's actually traveling here to Ottawa, and then we'll be traveling around US and Canada afterwards. But it'll be really interesting to get a kind of a primer on how the European approach to how building design works and how they work towards decreasing the energy consumption of them. All right, thanks very much.
Thank you very much, Adrienne. We do have a tabletop this evening, and I would like to ask Clark Campbell.
I'm going to send Jenna.
And he's going to delegate it to Jenna. Jenna, if you could please come up and tell us about Belimo.
Okay. Got volunteered for the last minute. Can everyone hear me? Yeah. Okay. So over there at our Belimo booth today, we're talking about the continued evolution of the control valve. So what we're showing over there is pressure independent valves and why they're important in energy efficient systems as we move forward. So for those of you who don't know me, I am Jenna Lyons. I have been the Belimo sales rep in Atlantic Canada for the last 4 years. I took over that region from Clark about 4 years ago, and now I am basically moving in effective January 1st of this year to Ottawa and Gatineau as well, and he's not trained. Clark isn't going anywhere. He's staying on Belimo in a training capacity, so he will still be around, so you'll still see him, probably. Otherwise, you'll have me. All right, so come over and visit us, say hi to me, and see what we're doing over there. Thanks.
Thank you very much, Jenna. And Clark, we'll still see you here, right?
Yes. So I get to travel Canada coast to coast doing training The
Well,
next 3 years.
fantastic. But the third Tuesday of every month.
It's on my calendar.
I would especially put a shout out though to the students to check out the tabletop and see some of the advances in the industry. I mean, it's a cool opportunity just to get some exposure and see some of the new tech that's out there. So we are running a buffet this evening. So normally we would have Sandy here, and she'd be picking off this table, that table, the other table. But Sandy unfortunately is hurt her leg and is on crutches and won't be here this evening, or if she is, she's still trying to get here. But in any event, we will figure dinner out. Don't you worry. If you haven't yet seen Adam about RP raffle tickets, please do. And I figured that we're all a relatively civil bunch, and you're pointing at which thing?
I think this is a great table to start.
Well, see, I was going to say this one. I think I promised Gemma that you know what? How about we just sort of start feeding ourselves, and we'll just start with the table that's closest, and we'll figure it out. Thank you very much, everybody. Hi, everybody. Sorry to interrupt, but we are going to continue on with the evening. I'd like to get Adam Moons to come on up, and we'll do the research promotion raffle.
Thanks, Dan. Dan Redmond, everybody. So we want to thank Walmart Ventilation for donating 4 tickets and 2 parking passes to the Ottawa Senators versus Buffalo Sabres on March the 26th. That's on Tuesday. It should be a fantastic game and a fantastic experience for whoever happens to win. So thanks to Walmart for this. And if we could get our delightful speaker up to draw, and $611 was raised for ASHRAE OVC. So thanks to everybody here. Yeah, I didn't have a need to give change for the toonies. I got $6 in toonies and hanging over. Yeah, so if you would be so kind, sir.
I hope I will win.
I'm going to take the money out of the way just in case.
I just take one?
Take the right one. Oh, which one is it? That one? So our winning ticket is yellow ticket, 842-2970.
It's the stupid one. It's next president.
And our secondary, congratulations. Wait, oh, yeah. Congratulations. And we have an auxiliary prize as well. Thanks to Belimo for offering up this fantastic bag. And if we could get a draw on that as well. Come on.
We all
Work here is never
have
done. You know this.
I know how to do it now.
Winning ticket is yellow ticket, 842-2985. President Boyce. And thanks to everybody for participating in this today.
Thank you very much, Adam. And Daryl, I mean, for somebody who's going to be traveling the world, you get to travel the world in style, right? There you go. Looks good. We need some more pictures, right? Before he takes the hat off. So we will move on to the program portion of the evening. And I would like to invite Roland Charnot to come up to the stage. And as he does, I'm just going to introduce him. Roland Charnot from Pajot Morel is a professional engineer and an ASHRAE fellow. He is always strongly focused on designing energy-efficient buildings. He is without a doubt an outstanding figure by virtue of his humility, righteousness, professionalism, and passion for engineering. Throughout his career, he has left a significant legacy by mentoring and training a generation of young engineers. As a testament to his skills and the high quality of his projects, Roland Charnot has received more than 25 awards for projects he has worked on. 25. That's fantastic. Including 9 ASHRAE Technology Awards. The program this evening is the Mountain Equipment Co-op headquarters building in Vancouver, British Columbia, which won first place for the ASHRAE Technology Awards in 2018. The Mountain Equipment Co-op head office, located in southwest downtown Vancouver, is a new construction with timber structure and abundant windows, 10,000 square meters, home to more than 375 employees, and includes administrative offices, a call center, a sewing room, and several labs. The new headquarters incorporates a series of energy efficient and sustainable development measures and resulted in a reduction of 43% in terms of energy consumption. 43% reduction in energy. Outstanding. Last November, the project also received LEED New Construction Certification at the Platinum level, which is the highest level of distinction for sustainable building. Roland Charnot, please come on up to the stage. Thank you very much.
So thanks, Daniel, for the introduction, and thanks you all for being with us tonight. Today's presentation is about Mountain Equipment Co-op new head office in Vancouver. The agenda of the presentation: first we'll go through a general description of the project, then we'll discuss about daylighting and its impact, the building structure, electromechanical systems, and finally the results of the project. I want to give special thanks to Hugh Caution, the architect of the project, which is with Proscenium Architecture in Vancouver, and Tanya Luti, which was the structural engineer to the project for Fast and Ebb. At that time she was in Vancouver. Actually she's heading the office in New York City. Just start with a few reflections. The first one, buying quality product is like buying oats. If you want nice, clean, fresh oats, you must pay a fair price. However, you can be satisfied with oats that have already been through the horse well, that comes a little bit cheaper. So it's like a feast. It's not like being in feast. The second reflection that I always have is the impact of the comparison between the building and cars. If today we decide to have cars which would consume 50% less energy than the actual cars, it's technically feasible. And in 10 years from now, we would reduce the energy consumption of the cars by 50%. But what about the buildings? What can be done if we decide to take a decision today? In 10 years from now, we cannot reduce by 50%. The idea of the building is there for so long time that we have to pay attention on how we design the building. The buildings are there for 50 years, 100 years, so we have to pay attention how we design the buildings to make sure that they are efficient. There's always solution. You can have a channels above a river. That's in Germany, the Magdeburg Channel. So there's always a solution to the problem that you can encounter. There is always a solution. You can have a pipe going through a pipe. So you have to pay attention to which pipe you put first. In this case. But these fittings are no more available in the market, so unfortunately, it would save space on some points. There's always a solution if you want to add drainage to a building or if you want to add a thermostat, but I'm not sure that the results are very well accepted by the neighbors or by the occupants of the building. There's always a solution if you want to cap the pipe. There's always a solution, and that's, in fact, it's in the Mountain Equipment Co-op project that I took this picture. We had to cap the pipe because we were doing some dirty work, so we find a solution quite quick, fix solution. So maybe the green building would be the solution. And there's all types of green building. That's the one. That one is green. That's an Ottawa building, in fact, which is all covered by green plants. Or maybe net zero building would be the solution. That's the net zero building that stays for many years. But maybe it's not, depending on what you are doing in your building. It can melt during the next few hours. So the reflection here is that the engineers, we are responsible of the situation where we are actually in the design of the building. Because we always like challenges. We always find solutions for the problems. When the architect gives us some problems, we were always able to solve it. If there is a building with 100% glazed, we are able to heat the building. If there's no window in the building, we are able to lit the building, to light the building. So if there's a column spacing 40 meters, we are able to find a solution to calculate the beam. So we always found solution to the problems that were posed by the architects. So why integrated design process is needed when doing new buildings? We find out that sequential approach doesn't give the optimal solution. Additional technologies does not solve the problem. We can add control, we can add technology, we can add cooling. We always multiply the technologies in the building, and the buildings were not efficient as they should be. And also the occupant behavior is very important. There's studies that has been done with different building exact two same houses, and the consumption of the building could be twice as much in some house compared to the other, depending on the behavior of the people, how they behave in their environment. Needs for high efficiency building. We need more and more of a high efficiency building. The climate concern everybody, and we have to work hard for the next years to solve the global warming of the planet. Why integrated design? Occupant comfort is mandatory, and more and more when LEED was developed, it was to reduce the impact of the building on the environment. Actually, we have a new, the WELL certification, which looks at the comfort of the people. We are building buildings not for building it, we are building buildings for people that will occupy the buildings. The other fact that we see actually there's more and more densification of the office building. There's more and less space per person in the building. So we need high quality environment for the people occupying the building. Owners and tenants are highly performing employees. The big expense per square meter of building, it's not the heating and cooling, it's the salary that you pay for the employees that you have in your building. So you have to give them very interesting environments to have them performing at a high quality level. So we'll go through the general description of the project. The integrated design process is based on the life cycle cost of the building. It starts on day one with all parties involved. What was interesting with this project, when we first sit Around the table, there was no line drawn on the project. Around the table, there was the owner, the architect, the mechanical engineer, electrical engineers, structural engineers, project manager, all around the table without anything drawn. That was very interesting to have everybody having a word to say on the development of the project. Try to optimize all the characteristics of the project. The process considered the design, for sure, the construction, the operation of the building occupancy, the environmental impact of the building, and the end of the building, the construction. Even at the end of the life of the building, the building can be reused for another function or can it be dismantled. So we try to see more than the initial use of the building. Vancouver, I was not able to translate this one. About Vancouver, which is green, and Vancouver, where there is a lot of buildings which are highly placed in Vancouver. The general weather data, Vancouver compared to Ottawa, for the heating degree days in Ottawa is about 4480 degree days, in Vancouver 2670. So there's 65% more heating demand in Ottawa than in Vancouver. So it's important to remember that. We'll see how it has been considered and what's the difference of design of the envelope of the building compared on what we're doing year round. Degree days of cooling, there's much less cooling in Vancouver. The exterior temperature again is higher for heating and lower for cooling. Bright sunshine hours, it's 1784 in Vancouver and 2084 in Ottawa. The major difference is that the 1784 is mainly concentrated in summer days, during the summer. June, July, and August, the 2084 hour, the 1784 are mainly in summer. The rest of the year there's a lot of clouds and rainy days. The site, which is, we have the downtown Vancouver, which is in this area here. It's quite a little bit further away from the downtown Vancouver. It was a site which was already used by an old industry of fish transformation. And that's the existing building which was here, which was an old industry which were transforming the fishes for distribution. And there's the Central Valley Greenway, the Green Northern Way here. And there was a parking just across the street. And the site was an old dump, an old field site. And when they start excavating, they find all sort of bones and everything in the ground. So the ground in this area is of very poor quality for structural purpose. The soil was very, very bad. The building, as described by Daniel earlier, it's about 10,000 square meters, mainly for offices and other use in the building, 370 employees in the building. And the main objectives of the client for this project was the occupant comfort. They were occupying a space, actually. It was not very bad. There was a glazing, etc., but they have to move because they need much more space. It was too small and there was no way to expand where they were, so they had to find another location with more space. So they decided to build a new building. But their consideration was mainly for occupant comfort. They wanted to have daylighting, view to the exterior, indoor air quality, thermal comfort, acoustical comfort. So it was very dedicated to the employees' comfort and also energy efficiency, which Mountain Equipment Co-op tried to do very efficient building when they are designing new construction. Thermal comfort parameters, it's interesting to remember that and we bring it at the table also. The comfort parameters, what makes us comfortable in the room, it's not the air temperature, it's mainly the radiation. We are comfortable actually in this room, not because the air is at 21 degrees C, it's because all the surfaces are at 21 degrees C. So the radiation component is the main parameter of the comfort when we are in the room or in the space. Air velocity movement and convection around us is about 26%. So when there's an exterior wall with a cold surface, we rapidly are uncomfortable due to the radiation, which is the major component of our comfort. So we have to work to have a higher exterior surface temperature in winter to make sure that people are comfortable. Now about daylighting and its impact. So the first step that we looked at, we tried to reduce the energy consumption of the building. And the first step was to look at reducing the electricity need, because electricity is a very high value energy. Electricity can be used for lighting, it can be used for welding, to run motors, it can do all sorts of things. So using electricity for heating is not a very good way to spend this high quality level of energy. So the first step was to work on daylighting. So all the team decided that the first step that we would do would be to work to increase daylighting or having good daylighting in the building. So the result of trying to have daylighting throughout the building, the impact of it is that it creates elongated building. If we want to have everybody to have daylighting, we have to have long building because the width of the building is limited. If you want to have daylight in a portion of the building, you can have about 20 feet or 6 meters of daylighting on each side, plus a central part which can be used for a function. So you are limited to about 18 meters wide to have daylighting in the building. So for the 100,000 square feet or the 10,000 square meter that we have, it would mean that the building would be, if it's only one story, the buildings are very elongated. And it's a real impact when we're doing the building. And unfortunately, when we do simulation, energy simulation, the reference building is the elongated building. We don't look at what would it be if we would have a square building. So the height was limited to 4-story because the owner wanted to have an active interior displacement. So if we have a 6-7-story, people would start to use the elevators. So at 4-story, he demonstrated that if there is a very attractive stairway, the people would use the stairwell. So the daylighting also defines the profile of the building. It defines the daylight penetration and defines the height of the building. In this case, it was for the 3-story above ground floor, it was 4.5 meters, and the ground floor has been established to 5.2 meters. So the daylighting defines the length of the building and defines the height of the story to maximize daylighting in the building. So doing that, we've done all sort of simulation for daylighting to make sure that there was sufficient daylight penetration in the building. And instead of having a very long building, as we said, it was decided to have 2 parts of the building interconnected together. So there's 2 parts per se instead of having a very long building. And the central part was the general communication part. The stairwell in the center to have communication between the different departments and the different story of the building. And there was also a simulation made to see what's the daylighting penetration, how to reduce the glare in the different stories, etc. So the next step when you have work to have enough daylighting is to try to reduce the direct sun gain in the building. So the next step was to develop outside overhang to reduce the penetration of the solar rays and the heat loads, the cooling loads in the building. So that was the next step that was worked out to reduce, again, to try to work as passive as possible. So daylighting, we develop the windows, but windows in summer creates you problems, so you have to solve the problems with, first with exterior overhang, and the second step was to install roller blinds. And roller blinds, the roller blinds are split in two parts. The upper parts, it was decided to have motorized motor blinds, which are closed depending on when there's direct sunshine, the roller blind closed, and when there's no direct sunshine, then the blinds opens. And if tomorrow morning you look at the different building around, you will see that the blinds are almost 50% are closed in the building. Because when there's direct sunshine, people close the blinds and they never open it up often. So it's detrimental to efficiency of the lighting if the blinds are down. So if you want to have a very efficient daylighting, you have to motorize the blinds to have it up when there's no direct sunshine. And the owner, also there was discussion in the lower part of the blinds, it was decided to have manual operation of these blinds, because this part of the window helps for daylighting, but helps for the people which are nearby for daylighting. And the upper part works mainly for people which are away from the windows. So that's the end results of the daylighting. You see that the large windows, and you see that there's operable windows for natural ventilation. And we will discuss this a little bit further in the presentation. So the point was, as said earlier, when we are developing the building for daylighting, if we compare the building with daylighting with, I would say, an optimal building with a square shape, there's 53% more perimeter with the daylighting, with the elongated. And that's never taken into consideration when we do energy simulation, because the reference building is the building that we are doing. So there was discussion with the team, and we said to the owner, it's not the best way. So for a traditional building with 40% glazing, we would have a UA factor of 8,264. In our case, before improvement, with 47% glazing, 53% more envelope, we had a UA factor of 22,074. It's almost 3 times more losses with our daylighting decision. So we tried to discuss how could we improve this situation. Then we worked and we made simulation, and we see that the reference, the heating, even if it's in Vancouver, the heating was the biggest part of the energy consumption of the building. So the first step was to try to improve the windows. So it was decided to go with triple pane windows in Vancouver. We know the climate is quite mild there. So we decided to go with triple pane fiberglass frame with an R3.7 thermal resistance. That's including the frame, etc. So it's the global average of the whole glazing and frame thermal resistance. And to justify this decision, we looked at what would be saved. Having these high efficiency window, we saved 24 tons of heat pumps for $60,000, 7 boilers of geothermal, 150 square meters of radiant panels for a saving of $178,000. And for the 2,100 square meters of glazing, it was $85 per square meter. The additional cost for triple pane is $86, so it was a wash. The savings that we were doing in the mechanical system compared to the triple pane pays by itself, plus we had an annual saving of $7,100. So it justified to go with the triple pane glazing in this case. For the walls, it was decided to go to the structural insulated panel, the SIPS panel. It was not used as structural, it was used as part of the wall. And it was decided to go with 300 millimeters or 12 inches of insulation, R50 for the walls. So again, it's quite a step to improve the envelope of the building. For the roof, went to R70 with polyisocyanurate insulation at R70 for the roof. So if we compare with the model code, the National Energy Building Code, ASHRAE 2007-2013, we have a resistance of, for the roof of 12 compared to 4, 5, 3, 4. So we are almost 3 times better than the reference. For the walls, we go to 8.8, so again, 3 to 4 times better than the reference. The windows, 0.65, so it's about 1.8 better windows. It's a big challenge to improve. There's a limit. The availability of high efficient windows are limited, and I think there will be some improvement in the future in that field. That's a big lack in the building envelope is the windows. So now if we look at the building structure of the project, again, around the table there was discussion about what should we use. Should we use the wood? Should we use concrete? Should we use steel with steel deck and concrete on top? Or should we use steel with hollow core prefab slab? So there was 4 options that were evaluated and costed. And there was not a big difference between the different options. It was about 2.5% difference in cost between the options. And what made the decision easier, it was the weight of the building. Because with all the options, except with the wood, we had to put piles. The ground was of very poor quality. And if we would go with concrete or steel with concrete slab, etc., we would have to install pipes, which would have been quite expensive. So the decision was to go with wood. There was 2 reasons. There was the cost of the pile, which was involved, and also the wood is available locally, and it's also the sequestration of carbon with the wood construction. So the decision was to go with wood. And the wood construction, the basement and the ground floor is concrete, and then the rest of the building is wood. The 3 and 4 story is with wood, with columns of wood and beams which are also woods, and we have the columns, and there's beams on each side of the columns at each 20 feet. It's a 6 meter by 6 meter grid for the building. And you see that the beams and the columns are protected for the rain, because there's quite some rains there in different periods. And the floor comes in what we call wood slabs, which are 4 feet by 40 feet long. And they are installed staggered, so there's 20 feet staggered installation of the wood slabs. And it's not cross-laminated timber. Cross-laminated timber is timbers which are in different orientation. These ones are nail lamps, so it's 8-inch planks which are nailed all together to create the slabs. Again, there was the cost analysis that were done, and it was cheaper to have these nail lamp slabs done instead of CLT in this case. And you see the screws that drives down to the beam. So you need some quite good tools to put these screws to put it in place. time. So you see the different slabs which are installed, and you see here the columns that will go through, and you see the two beams which are on each side of the columns, and other columns on the other side. And here the next step is to put plywood on top of these planks to create a diaphragm, to have all these slabs work together to attach and make it as one floor, one slab. So the next step was to put all the plywoods on top of the planks. Then it was decided in the discussion to have displacement ventilation, to have a plenum, to have displacement ventilation in the floor. But as soon as you use these space as duct or air supply duct, it has to be ignifugated. It should not be combustible. So the decision was to pour concrete on top of the plywood. So before pouring the concrete on top, we decided to put all the conduits for distribution, for electrical distribution and data distribution in the raised floor. Then the concrete was poured on the floor, so it makes also a neat surface for the workers to roll their equipment on the surface. And it was quite easy to have them work on the surface. Then it's wood construction. There's some rain. There was some schedule that was moved. So part of the construction, instead of being in the very nice sunny days, or it went later in the season, and there was a lot of rain. So it was decided to put some temporary weather protection. And that's a common practice in this area in Vancouver, to have a protection, build big tents above the project, and it increased the number of potential working hours instead of having rains and delays of work. So that's a common practice there. So that's the roof level, and here what we see is the ventilation, top of the ventilation tower, we will discuss later on. It was protruded above the roof surface. Potential rain impacts, there's some leaks, and there's some work that has to be done to correct leaking and stains on the wood. It's not a big deal. It's quite easy to sand it and to eliminate the stains on the beams. So that's about the part of the structural. Now the electromechanical system for the project. The conceptual approach that we had with the team first was to create a high efficiency envelope. And as discussed earlier, the envelope of the building is there for so long time, for 50 years, 100 years, and it's quite hard to improve an envelope of the building. For the mechanical systems, after 20 years, 25 years, it has to be replaced, it can be improved, it can be modernized, it could be, the controls can be optimized, modified, but for the envelope of the building, it has to be done well the first time. So the first step, as discussed earlier, it was to have a very efficient envelope, and at the same time, it reduces the capacity of the mechanical system. Then to use passive methods for lighting, we discussed it earlier, for heating also, because in winter the sun is lower and it penetrates in the building and it helps for heating. Ventilation, we worked with hybrid ventilation. We will discuss this later on also. And next step is to recover all energy losses, energy from artificial lighting for occupant, from daylighting, so all the energy sources, all the losses in the building has to be recovered for heating later on, or in other facade of the building. Use of high efficiency equipment for artificial lighting, for motors, for transformers, etc. Try to use the most efficient equipment available. And what is interesting here is to accumulate excess energy from one period to use it on a later period. During the day, there's occupants, there's computers, there's lighting, so there's, and with a very efficient envelope, there's often excess energy during the day. And at night, we need energy, so why not find a way to accumulate this energy to use it later on. Neighborhood inspiration, it's about the natural ventilation. That's an old device when it orients with the wind, and the air comes on the small end here and goes down in a central pipe. These pipes, there's two pipes. So in the exterior pipe is the exhaust, which is exhausted on the inward side of the wind. So the same device makes air, incoming air in the building, and it's exhaust air at the same time with the same device. So what we try to do in this building is to have what we call natural hybrid ventilation in the building. So in discussing with the team, we decided to have 3 ventilation shafts in the building. 6 meters by 6 meters each of these shafts. So we have very low velocity in this shaft. We are about 100, 150 feet per minute. Very low velocity in the shafts. And what we do is that having the wind blowing in the shaft, the air goes down in the mechanical room, is filtered, goes up in the raised floor, and then back in the other part of the shafts, and is exhausted on the other side. And on the tower, there's dampers on each facade of the dampers, and depending on the wind station, the weather station, we open the dampers on the right direction, depending on the wind direction. And there's still fans because there are some days there's no wind. So there are small fans to continue the process when there's no wind. That's a very interesting process. And what's interesting with this, at the beginning there was discussion about opening the windows, but opening the windows is not very democratic. You know, the people which are nearby the windows open the windows, and the people in the center have no control in it. So having this type of system, you distribute the air when the conditions are right, which are quite often in Vancouver, and you distribute fresh air uniformly to everybody. So we made some CFD simulation to make sure that it would work, and it was working in the simulation, and it works in the field. The raised floor, which is used as plenum, it's an 18-inch raised floor, and as seen earlier, the conduits which are in the slab, poured in the slab, feeds distribution box with quick connects, which feeds the service box on the floor. So when you want to work or modify the environment or displace the workstation, you can unplug. You don't need an electrician. You can unplug the service cord and move the service panel to another user. And also the surface of the concrete tiles on the raised floor are of concrete, and there's no carpet. The owner, and after discussion with the team, it was decided not to have carpets for quality, to avoid dust and stuff in the air. So it was concrete, and there was a question about the noise. The people and the people pay attention to the shoes that they wear to make sure that it doesn't make noise. They are all employees of the same company, so they are very conscious about the others, so it works very well. And another concern, there's no perfume. People are not allowed to use perfume in there. So again, to maintain high level of indoor air quality in the building. The return, you see the return are again at very low velocity, about 100 feet per minute, and instead of having square corners, it's very, very smooth corners to reduce the losses, so there's almost no losses in the return system. You see also the sprinklers are in view, and again there was a long discussion, should we put the sprinklers in the raised floor and drilling it down to the other level. But at the end of the day, it was decided to put it in the same floor, because for retrofitting it would be easier to have access to the pipe instead of working in the raised floor and having water in the raised floor and contamination, etc. So that's the radiant heating and cooling. So all the envelope load is taken by radiant panels. It's radiant sails, it's about 5-inch wide, and these panels are supplied by hot or cold water with 6-way valves, so there's no cross-contamination between the two networks. So there's radiant panels which takes care of the envelope load. The cooling, the heating of the envelope is taken by the radiant, and the internal loads from people and lighting is taken by the air supply from the raised floor. We said earlier about the energy accumulation. To accumulate energy, what was decided was to use thermal tanks. So on the cold side, we have 4 tanks of 11,000 liters. So we have about 10,000 gallons of potential energy accumulation on the cold side. On the hot side, we have 1 tank. In fact, it could have been reversed. It was decided to put it on the cold side because the process is that during the night we would cool the water, which are in the tank, to heat the building. And in the morning, the water would be cooled and would be used for cooling of the building during the day. So that was the thinking. So what we do, we use to feed the radiant panel, we use the hot water from the hot water tank, or on the other part of the building, we can use cool water to cool the radiant panel, to cool the building. And we have thermal tank regeneration. If one side is depleted compared to the other, we start the heat pumps to transfer the heat. For the building, we have 8 heat pumps of 10 tons, so we have 80 tons. It's more than 1,000 square feet per ton. It's quite efficient. I think it's 1,200 square feet per ton in this building, instead of the figure that we often have of 400. So it's 3 times less cooling equipments in the building. So at a certain point, the hot tank will be too hot because there's not enough demand on the heating side, or on the cold side, it can be too cool because we have a lot of needs on the hot side. So what we do, if the hot tank is too hot, then we drive the hot water in the ground loop. So we have 21 wells to reject the heat in summer when there's excess heat, or in winter. In fact, the wells are the same. It's shown different wells, but in fact it's the same wells which are used in summer or in winter. So again, in winter, when we extract too much heat in the tank, the water comes too cold, then we start circulating this water in the ground to extract heat from the ground. And in this installation, there's no glycol or antifreeze. It's direct water, so there's no risk of contamination. And it impacts the number of wells because we need more wells because the temperature that we draw in the ground is not cold as it would be if we would have antifreeze. But it was a decision again that was taken not to have antifreeze and no risk on the contamination of We also have a heat recovery on the shower drain. There's a lot of people in Montreal who would go up. Almost every person comes to work with bikes. There's a lot of bikes, there's a lot of bikers, and there's a lot of showers. So we put heat recovery power pipes, and the showers are on the ground floor. So on the basement we have power pipes to recover the heat from the shower drains. Which is particular in Vancouver, they didn't know this device, they didn't accept this device, and we have to fight for several months to have them accept this to be installed. And they asked to have some notes on the pipe, so do not repair if damaged, leaking, do not paint, cover, or alter. We had to put this sticker on the device, because they had fear that the rainwater would contaminate the incoming domestic cold water. So that's life. So it's quite a simple device which is very efficient. We have heat recovery on exhaust air, which is quite common. On the water side, we have a low flow fixture everywhere. We have waterless urinals. It's a standard with Montenegro. We have rainwater harvesting. On the roof, the water is harvested, filtered, and then goes to an underground cistern, which is used to flush the toilets to reduce the need of domestic water to flush the toilets. Then, what about the results? So, the result is very interesting. The reference building in this case was at $2 per square foot, and the proposed building is at $1.07 per square foot of building. Graphically, if we look at the reference compared to the proposed building, we see that there's a big difference in the heating. There's a lot of reduction in the energy consumption. Again, another presentation, the graphic, the reference, and the real building. What we see with the real building is that the demand is quite constant throughout the year, compared to having peaks and lower peaks. It's quite constant throughout the year. Here, this graph is very interesting because we add some meters at different points of the building. So here we have the reference, we have the model, and we have the measure in purple. So the lighting, we are quite lower than the reference, and the measure is a little bit over the energy simulation model. And what we find out is that there was a problem with the exterior lighting, which was on all the time. So this has been corrected. And another concern was about the plug loads. We had the reference and the proposed is always the same for the plug loads, but we see that the real case is 2.5 more energy consumption in plug loads. And what we find out is that they never close their computers. All the employees has their laptop or their computer on all the time, because it's a policy of the company to have all employees to be able to access their own computer by VPN at all time in their C drive. So that's a big difference in energy consumption. Even though we are 48% less energy consumption, even if there is these type of accident or operation, and that's what I discussed about the occupant's behavior. That's part of the occupant behavior and the fact of life. We have to live with that. For heating, you see the difference. That was the reference, the model, and the real, which is quite lower. The cooling, which is higher, mainly due to the plug loads, and also the cooling. Cooling includes part of the heating, because the heat pumps are measured. Sometimes they are doing heating, sometimes they are doing cooling, sometimes they are doing both at the same time. So the cooling and heating is it's not easy to monitor with the heat pump. We put sensor to find out if we were in a heating mode or if we were in cooling mode to try to measure separately, but sometimes it's own boat, so it's not clear where the energy metering goes. The pumps are lower, the fans are lower, and domestic hot water, again, it is lower than the reference, but it's quite higher than the predicted. Again, it's the number of showers that are used, which was not the right figure that we had. There's more users of the showers than was predicted. But it's interesting to have the different metering. When we're doing building, we try to have more and more sub-metering for the building to find out what happened in the building and try to correct or understand or react to what can be done in the building. So the end result is the building here, which I Google view. And we see here the old fishery building. This part was demolished. And at a point we were thinking to reuse some very nice BC for beams that were in the fishery building, but it smells too much. There was no way to reuse it, unfortunately, because there was very extraordinary structure and beam in this old building. It was not possible. So that's the two aisle of the building, and there's a few parkings here, and all the water of the parking drains in the central pond, and it drains down in the ground instead of rejecting it to the sewers. That's the end result, and you see the ventilation towers, natural hybrid ventilation towers on top. Again, another view. That's a ventilation tower. That's that part of the building is 3-story, and the other part is 4-story. So at this level, we go directly to the exterior terrace when they do some barbecue or some activities, and on the other side is the cafeteria. And here's the ventilation tower of the 3-story building. That's the access to the terrace, the 3rd floor from the cafeteria. That's the cafeteria, which is the low velocity return. And we almost don't see any mechanical system. There's no ductwork, there's no boxes, there's almost nothing. So one point that I was discussing with Jim, they have some visitors of other building that want to do new construction, and they feel very, very good in the building, and there's almost never comments on mechanical system because they don't see anything. But that's the real purpose of the building, is to be happy in the building and be well in the building. It's not to see the equipment. And we see some diffusers in the floor diffuser, which are only manually operated. That's all the working station has adjustable height for working station. You could work seated, or it's all motorized working desks. They have collaboration space in the intersection of the two aisles of the building. There's collaboration spaces. There's interior offices. Mainly they have some interior offices. It's mainly for the buyers because they are quite loud-speaking people at some times. So there was a request at the early stage of the design to make sure that it should be confidential, and they have their closed offices. So that's in the central core of the aisles. That's the meeting room and the interior space. Again, there's closed office or meeting rooms. So meeting rooms, again, it's all glazed, so they take advantage of the daylighting everywhere in the building. That's the sewing room. Again, they were very interested to have daylighting to recognize the code. It was a very high color rendering with daylighting. Cannot be better than that. meeting room. And there's much more glazing in this part. There's climbing walls in some parts. So they are selling climbing equipment, climbing gear, so they try to use it in their own building. That's an open space. It's very interesting. The view is interesting. Daylighting is interesting. You see the radiant panel, small lighting fixture. All surfaces, all working surfaces are white to diffuse daylighting and artificial lighting to make sure that the lighting is distributed everywhere. And you don't see it, but all the surface of the wood ceiling has been whitewashed with stain to have it a little bit lighter in color, again to reflect light. It's not perfectly white, but they try to have a lighter surface. That's a diagrammatic presentation of the different systems. The ventilation tower, you have the radiant panels, you have the thermal tanks, the heat recovery unit, etc. The raised floor. So that's an interesting integrated view of the systems. We're discussing of a triple pane, and there's another building that has been built in Vancouver with triple glazing. It's a 31-story office building, 372 square feet, 240 millions. It has been built or financed by Credit Suisse, and they have a tendency to think of a long-term approach. So it's interesting to see that they did it with a curtain wall of triple glazing. So doing that in Vancouver, we are questioning why we have so much difficulty to sell triple glazed windows in the Ottawa or Montreal area. I think we have to work hard to develop this. In conclusion, what we see is the building envelopes are increasing with daylighting. That's what we see in the building design that we are doing. And at the same time, there's a reduction in internal loads. The lighting is decreasing. When I started doing design, we had 25 watt per square meter of lighting load. Actually, we are at 8 watt per square meter, 9, 7, 8, 9, in this. So they're decreasing load. So we are increasing the envelope, and we have less internal load to compensate for this. So that's a problem. Computers, again, are more efficient. Laptops consumption reduces. Building labeling will probably help. That's an ASHRAE BEQ will develop and will help when the building will be labeled. People will pay more attention to what they are doing. I'm questioning here, what's the value of the building that we designed? What would be the value of a building which is single glazed? Actually, there is still some buildings which are single glazed. They don't work much. So. The buildings are built for a very long period, so what we try to do when we're discussing with the team, if the building is there for 50 years, we should design a building that in 25 years from now, it should be according to codes of that time. I don't understand that we are building a building which will be outdated when the construction will be finished. That's what we're doing actually, so it doesn't make sense. So we have to speak up with the team and try to have another type of reflection. We are building the future, not the present. We should think to the future. And that's what it is. Yes?
Yeah, with all the wood construction, how do you manage the moisture in the building to keep it from getting too dry in the winter or too damp in the summertime?
What is fine with the Vancouver climate? is that at every night the temperature goes down. And it's about 100% humidity, but the temperature is low. When the temperature goes up during the day, the percentage of humidity is correct. Between it's below the 60% when it heats to the 21. So there's no real moisture problem. There's a lot of rain, so for the exterior surface of the building, it's a problem. There's a lot of rain. But for the indoor air quality, there's no problem, and there's no humidification too. So it's interesting with the outside air itself. It's correct when you bring it to the interior condition. It's like in the comfort condition.
You said that you deal with the envelope modes cooling with radiant panels, and you cool internally with the ventilation shafts. On your design day, your cooling design day, is there any other cooling happening there, or?
Yeah, yes. In the shaft, at the bottom of the shaft, there's a filtration, but there's also cooling coils. Yeah. For the peak days. And when we are in the peak days, the peak heating or the peak cooling, we close the dead burrs on the towers, and we recirculate, and we have the heat recovery. We have a minimum outside air, which brings air in the shafts.
Okay.
But there's more than, I would say, there's more than 60% of the time we can work with the hybrid ventilation. Yeah, but yes, we have additional cooling. Yes.
With the solar gain, or should I say daylighting, it seems as though the depth into the building as to which the sunlight can penetrate limits you as to how wide the building can be. I wonder what the opinion would be with regards to solar conduits, the solar conveyance technologies that could kind of take light from the center of the building and kind of disperse it.
Yeah, there's some technology which I've seen many years ago with fiber optics, with concentrator fiber optics bringing lights everywhere. There's deflectors to the exterior walls, or that can bring some lights deeper in the building. That's things that exist, but in this case we looked at different option, but there was the 2 points. There was the daylighting and there was the view also. The people wanted to have views to the exterior mountains, etc. So that was the. But it's true that for daylighting, we're bringing natural light deeper inside. There are some technologies that exist. Yeah.
Just kind of further to that question, what was the final compass orientation of the building? What direction is north on the site?
The south was there. The north was up. Yeah. Yeah. So there was no big glare control on this side. On this side, it was not far away from due south. So with outside overhang, it was doing the job. But in this orientation, it was more problematic with the sun coming in the morning. But we looked also to have vertical fins, etc. But at some point, it didn't fly. We cannot have everything in the building. That's a point which is interesting also during this type of integrated design process. Everybody has a word to say, but at a point you have to take decision. A design is a lot of compromise. Every time you have to take a decision, it's a compromise. If not, you would go straight on the road. But everything you have to take a decision, it's a compromise. You take one direction, but you left something on the side. And what is important is to remember on how, what do you consider when you take the decision. You have to come back to the objective of your project. The objective of this project was the comfort of the occupants, the daylighting, the view, etc. So when we're discussing about options, so vertical fields, does it impact the daylighting? Does it impact the comfort of the occupants? No, there's another way to do it. So it's all when the objectives are clear, it's easier to have a consensus around the table. And that's very important to make sure that everybody understands that. Because if not, we will be frustrated all in the process. But having the understanding of why you do these things is very, very interesting to have a project of this happen. I think it's one of the most interesting projects I've done in my life, to be so deeply involved in that decision. Yes?
I could ask questions all night. I'll try and limit myself to just the last one. About how many CFM of air can you move through this building? And what's the minimum outdoor CFM you're working with when it's full?
The total CFM is about, not far from 100,000 CFM, a little bit less than 100,000 CFM. And the minimum outside there is about 20,000. When we are in a recirculation room and we work with the mitigated ventilation system.
So, how do you make sure you're providing enough ventilation to like a meeting room if you're mixing the system?
The meeting room, there's in the general open area, it's the plenum. It's distributed by the plenum with the control. In the closed room, we have small fans that takes air from the plenum and bring it to the diffusers in the room. And for the meeting room, a large meeting room, it's the same. We have a small fan. The problem with the raised floor or displacement ventilation system, it works well in open area. It works well. As soon as you close a room, the air doesn't want to go there because there's an effort to be there, to go there in the closed room. So you have to put some fan to force the air to go in that room. And it's controlled by the thermostat control the speed of the fan to bring the air in these rooms. So if you don't do that, the pressure in the room is very low. It's less than 0.1 inch. There's not much to do with that.
Any other questions?
3, 2, 1.
Thank you very much. We'd like to present you with a token of our appreciation.
Thank you very much.
Here, I'll give it over to you. Thank you. Thank you very much, Roland. I thought it was very interesting to see how much more energy we put into heating and cooling here in Ottawa, but I was delighted to see that at least we get more sunlight. We did something, right? That's why we're here, right? No, thank you very much, Roland. That was fantastic, and some amazing ideas there that people can consider implementing into other projects. So just some closing remarks as we close out the evening. The next meeting is April 16th. It will be here again. We have Bjarni Olafsson, the former ASHRAE Society president, will be here speaking. The following day, April the 17th, we have the seminar that Adrienne mentioned on the European design, so innovative ideas that what is Europe doing, what sort of approaches are they looking at, and what can we learn from them? Everybody will be receiving a survey reminder. Please do take the time to fill out those surveys. It doesn't take very long. It's maybe a minute. I think it's 4 questions. But the information we get from that helps immensely in regards to building the future programs. And one final thing that I would just like to put a question out there to everybody. How many of you work on projects? Not a lot. Okay, it's not a trick. I'm expecting to see a lot of hands. How many of you think that your projects are innovative, though? That you're really trying to push the envelope, trying to do something different than the other guy, trying to go the distance? I'm hoping to see the same number of hands. Again, it's not a trick. But what I want to get at is the ASHRAE Technology Awards. So Jacob isn't here this evening, but we are going to be holding the chapter level technology awards. I believe the due date has been extended, I want to say until May, at the chapter level. And in order to be recognized for an ASHRAE Technology Award, you apply at the chapter level, and there are 19 different categories. And the winners then go on to the regional competition, and the winners from that go on to the society competition. What you just saw was a society-winning project. So what better way to commend yourself for the effort that you have done, to show the world that you are really pushing the envelope, to show your customers and your clients about how much value you can bring to the table than to submit for these. So I encourage everybody to take the time, consider submitting for the Technology Awards. The chapter level is not a very onerous process. And if you have any questions, please let me know or reach out to Jacob Huff. And with that, I'm going to close it the evening. So thank you very much, everybody, and thanks again, Roland.